And then we've got x squared equal, or plus 4.2x. I'm just going to put this in terms of the quadratic now. 4.2x minus 5.9 is equal to 0. Okay, and so I want to take this quadratic equation and solve for x. I'm going to get two roots for x. One will be real, the other will not be physically possible. That's always going to be the case. When I solve the quadratic equation, I'm going to get two solutions, but one of them will not be physically possible. So we'll look for that later. Now at this stage, we're all set to go. If you have a graphing calculator, you can just simply plug in these numbers. If you don't, you'll need to apply the quadratic formula. If you don't remember how to do that, there's another tutorial that you can look at to see how to do it in detail, but at least we'll go ahead and set this up for you. In this case, our coefficient A is 1, our coefficient B is 4.2, our coefficient C is 5.9, minus 5.9. And so just to remind you, the quadratic formula, let's write it in a different color. The quadratic formula is minus B plus or minus the square root of B squared minus 4AC, the entire thing over 2A. So I want to plug in my values for A, B, and C into the quadratic equation. And we end up with, in this case, 4.2, I should say minus 4.2, plus or minus the square root of 4.2 squared, minus 4 times A, which is 1, times C, which is minus 5.9. And I'm writing kind of small to fit this all in here, so if you look at our graphic, you'll be able to see my numbers if you can't quite see what I'm writing. And then we've got all of that divided by 2, A, and A is 1, so I'll put that in there, but 2 times 1, remember, coefficient is just 1 here. And so plugging this in at this stage and solving, we end up again with two solutions, the plus and the minus. One of these guys, notice that this is a minus number, a negative number. So the solution for minus a value here, that's going to end up being a negative value. And we can't have a partial pressure be negative. That's not physically possible. So we're going to throw out that root and take only the root that gives us an overall positive value in this case. And that positive value turns out to be x is equal to 1.1. And this is in terms of atmosphere. So that is the way we've defined it, the partial pressure of CO. And so the only thing else that we don't know is the partial pressure of CO2. And that is the total pressure, 1.4 atmospheres, minus the partial pressure due just to CO. And that gives us a value of 0.3 atmospheres. And again, that's our partial pressure of carbon dioxide. So we've done it. We figured out partial pressures both of CO and CO2, not knowing initial partial pressures at all, not knowing final partial pressures. The only thing we knew was the total pressure of the system and, of course, our trusty equilibrium expression, equilibrium constant, that tells us where this equilibrium is going to lie. So gases are not the only place you're going to find these types of problems. You're going to encounter situations where you'll need the quadratic formula in solution problems as well. And the strategies that we've presented in the last few tutorials still will apply to solutions. There's nothing different there than what we've been doing with gases. The only difference, of course, is that the units are different, and so the equilibrium is going to be expressed in different terms. But as long as you remember the law of mass action, which is what all of this is based on, then you can't go wrong. It's just a matter of using your head, thinking where the equilibrium is before you actually start the calculation. Let me just remind you one last time, because this is so important. Look at the equilibrium constant before you calculate. Determine if the equilibrium constant is very large, that means the equilibrium is far to the right. If it's very small, that means equilibrium is far to the left. In either of those scenarios, you're going to be able to approximate, more than likely, and simplify the math quite a bit, because you'll know very close to where equilibrium lies. It's the situation where k is close to 1, in the range of, let's say, 0.1 to 10, that realm, where you're going to probably have to do an explicit calculation with a quadratic formula, or it could be even worse in some situations, although you probably won't be asked to do that. So again, just summarizing here, the equilibrium constant gives you that information about where equilibrium lies. By knowing that information and knowing something else about your system, the total pressure at the end, the initial partial pressures, you're able to figure out all concentrations at equilibrium.